Ever wondered how long it would take for your money to double, or even triple or quadruple it? The answers might surprise you, using just the rule of 72, 114, and 144. These simple rules divide the numbers by your annual return rate to estimate how long your money takes to grow. At an 8% annual return, these rules show it takes 9 years to double, 14 and a quarter years to triple, and 18 years to quadruple your money. Now, let's dive into the rule of 72 to uncover how and why it works, and its limitations. It's all powered by an extraordinary financial principle: compounding. It's the cornerstone of financial growth, transforming small investments into exponential wealth over time. A represents the future value, or the total amount after compounding. P is the principal, the initial amount you start with. R is the annual interest rate, expressed as a decimal. N is the number of compounding periods per year, and T is the time, measured in years. Now, let's simplify this by focusing on annual compounding, with N set to 1, where returns accumulate once per year. Let's see how it works with a principal of $10,000 and an annual interest rate of 8%. With each passing year, the future value grows. At 9 years, the total reaches approximately $19,990, almost doubling. But let's also check for 10 years. At 10 years, the value moves farther from exactly doubling the principal. But at 9 years, it's spot on, perfectly aligned with the doubling point. The 9-year mark aligns closely with the rule of 72's prediction for an 8% return. Now, let's back it up a little to the formula and dive into the math to explore how and why this works. To double your money means the future value becomes twice the principal. Accordingly, we substitute A equals 2P in the formula. Next, we divide both sides by the principal. Then, we take the natural logarithm of both sides. Using logarithmic properties, we rewrite the equation. Now, we isolate the time variable. Substituting natural log of 2 as 0.693 gives us a simplified expression. We further approximate natural log of 1 plus r, with r for smaller values of r. This simplification comes from the Taylor series expansion, where the natural log of 1 plus r is broken into a series of terms. Since the higher order terms become negligible for smaller values of r, we focus only on the first term. Notice that the interest rate, r, is expressed as a decimal. To make it more intuitive, we convert this decimal into a percentage by multiplying it by 100. We notice the value 69.3 in our formula, but instead of using this exact number, we adjust it to 72 for simplicity. This adjustment allows us to perform quicker calculations while maintaining practical accuracy. We'll explain the reasoning behind this adjustment in a moment. Now, let's focus on these steps. By adjusting A equals 2P for doubling, we can extend the concept to tripling A and deduce the rule of 114, or even quadrupling for the rule of 144. This demonstrates how these rules generalize to different growth scenarios, offering insights beyond just doubling. Let's take a closer look at this graph. It shows how our approximation for R works in practice. You'll notice that for practical growth rates between 6% and 12%, the results remain highly accurate. However, moving beyond this range may introduce slight margins of error or reduce precision. Even so, values slightly outside this range can still be useful for quick calculations or rough estimations. We adjusted 69.3 to 72 because this is meant to be a quick shortcut, and 72 provides a wide range of factors, making it exceptionally useful for estimating doubling time across a broad spectrum of rates. Try applying the rule of 72 to your portfolio's average return rate and investment amount. Share your results in the comments. We'd love to hear your insights. Thanks for watching. See you in the next one.